So today I will talk about a specific topic. So today I wanted to ask the question, is AI the best solution for systems with unpredictable behaviors? And I will talk about a specific application for the force estimation using multimodal approach. So here I will present the multimodal approach as a solution to avoid some problems of artificial intelligence approaches. Voilà. Ça tourne. So I will start by the problem here. So here the problem is how we can estimate the muscle, the force of the muscle, without using complex models based on, for example, element fini and very high computing time. So here we can't cut the muscle and put a sensor. We can't measure the force of the sensor directly here in the muscle. So the solution here, it could be based on the artificial intelligence methods or data-driven methods. So before talking about the solution here and how we can estimate the force muscles using data, just the data, here I wanted to present some applications why we need the force estimation. So we need the force estimation for some biomechanical applications to estimate the gait, and also in the Parkinson disease here we need also to estimate the force of the muscle because we needed to have an idea about the rigidity, about the tremors, the changements, and the gait. So the force muscle is very, very important in this application, and also in the myoelectrical hand prosthesis. To propose a hand prosthesis for the amputees, we need to well estimate the force of the muscle, and here we know we have different kinds of movement. We have very, very fine movement like the writing, like for example the drawing, the painting, and we have movement more simple like open and closing the hand. So here, if we will propose a model based on the conventional models in mechanic like element fini, so here we need a lot of computational time, we need a lot of hypotheses, and if we will go to the data-driven models, so here we have also other kinds of problem because we need a lot of data for each kind of movement. So the idea here is just to find the relationship between EMG signals, the muscles activities, and the force muscles. And here why we wanted to find the relationship between EMG signals and the force muscles, because EMG signals, we can measure this type of signals just with simple electrodes on the skin. And we have a very high relationship between EMG signals and the force muscles. And EMG signals are electrical signals of the activities of the muscle. So the problem here in the literature, we can see that 80% maybe or maybe more for the intelligent prostheses that are based on the estimation of the force muscles from EMG signals are not very comfortable for the patient. So more than 80% of the patient don't use these prostheses based on the estimation of the force muscles just from EMG signals. This is one problem. And why we have this problem? Because, as I said, data-driven models are very sensitive for the changement of the data. And we know that EMG signals are very, very unpredictable. We have a very unpredictable behavior for these signals. So if we change, even for the same movement, we can have different kinds and different shape, different form of the EMG signals. So for these reasons, most of the patient don't use the intelligent prostheses, the myoelectrical prostheses that can estimate the force muscles from EMG signals. Because instead to open the hand, they will close the hand. Instead to say hi, they will say like this, no, or I don't know, another movement. So it is not very comfortable. So what is the solution? If we have a problem with conventional approaches, if you have a problem with intelligent approaches, what is the solution here? The solution here is, so here, before presenting the solution, I will present the problem of the complex system. So we know that nonlinear system, here we have a nonlinear operational space. Okay, we don't have a linear operational space. So here for complex system, we can have a very complex operation space. And if we can talk, and if we want to integrate a physical or white box model based on the physical equations, it will be very difficult to have a nonlinear model that represents all the operational space. Okay, so here, as a solution, as I said, is the black box model. Here we can have a different measurement of input-output, and we can try with different algorithm, intelligent algorithm for machine learning and or statistical models, nonlinear models, to estimate the output from the input. But here, what I want to present today is how we can divide our operational space, highly nonlinear operational space, into different operating points. And in each point, my system will be linear. So I will explain. For example, if I have a nonlinear system, I know that the nonlinear system can have a different operating point, and in each point, the system could be linear. And if I have a linear system, so I can propose more simple mathematical equation to describe the behavior of the system. And here the equation could be from the physical law or from input and output data. Okay. Alors, so here is the figure for the multimodal approach. So the multimodal approach is the solution to divide my operating space, complex operating space, into sub spaces that are simple and linear and simple to represent. So here I have three main blocks. The first one is the model library, and here I have a library of models. Okay, and each model here I can say submodel for each simple model that represent a specific operating point. So each model is represent a specific behavior of the system in a specific operating point. Okay. And then I have the output block. The output block is a block to do the fusion or the switching between the models, because here we can have two kinds to compute the outputs with the fusion or with the switching between the model. If I will choose the switching model, so here I have some problems, because if I will switch between one model to another, I will have problems of stability, the switching problem. But if I will propose the fusion, it will be better. But here I have also to know the adequate equation of a fusion and the best equation of a fusion, and it's not very simple here. Okay, it depends on the model, on the equations, on the submodels, etc. And then we have a decision block to define the and this block it communicates with the libraries and the outputs. Okay, so here this block compute the parameters that the output block will use to define the final output. Okay, so here I just want to to give you an example. For the first estimation here, we can have, for example, a physical model, very simple model, linear model. So here, as a first application, we can have in the library 3 models, for example. Each one represent an operating point according to this model. Okay, so for this model we can have, for example, for the first submodel we can have mass 1, for the submodel 2 we can put here mass 2, and here mass n for submodel n, and these parameters are physical parameters but can change for one person to another, or even for the same person, because the muscle of the human can change, because if you drink a lot of water, we can have a value, a first value, but if we don't drink, for example, a lot of water, or we will do a physical activity, also the mass will change. So here we can put for each submodel, we have the same structure, but the parameters will change according to the operating point, according to the hypothesis, according to the condition. Okay, and sorry, voilà. Okay, so this is the first one is based on the physical model, because this is a physical equation and the parameters are physical, and here the difference between submodels is just based on the value of the physical parameter. But now I will present another kind of library based on input and outputs, and here I have two kinds of data. The first one, here I have EMG signals, the muscles activities, and the force of the muscle. Okay, and in parallel also I have another experimentation that allowed me to have two kinds of data, EMG signals and the handwriting of the patient. So here the patient will write on a plane some letters, he will draw some shapes, geometric shapes. So in my base I have the EMG signals and the displacement of the pen, and in the first database I will have EMG signals and the force of the muscle. Okay, so here I can put in my submodels the first model, for example, that represent data 1, and then submodel 2 represent data 2, submodel n could represent data n. Okay, this is a combination based on input-output models. And also I can put in my submodels hybrid models. I will explain. So the first model could be based on physical model, but the second one could be also based on the data. Okay, so here I can mix between to take the advantage of the physical model, but also the advantage of input-output models. So here some examples of the multimodal approach for the first estimation. In blue is the real force, and in green is the ANN estimated force, and in red is the multimodal estimated force. And here why I use the ANN, because according to the literature, the ANN is the most efficient approach used to estimate the force muscles from EMG signals. And here we can see directly the difference between ANN and the multimodal approach. And the multimodal approach estimation is very close to the real force estimation. Yeah, so here this figure is very important. Why? Because here I have different scenarios, and if I talk about scenarios here, a different validation form. For example, for the scenario 1, we just put the same person, the same data for the same patient. Scenario 2, the same patient, but here in different condition, with different physical activities, etc., to change the parameters of the patient. the physical parameter of the patient. And in scenario 3 here, we use different patient. We validate our model with different patient, which is very, very hard. Why? Because we know that each person is unique, even for EMG signals, even for for the muscle composition, etc. So this figure show that the ANN approach here we have a variable R square here the plutôt statistical features for sorry. Voilà. Here the root mean square error for the three scenarios. So here we can see the difference and the variation of the ANN approach for the three scenarios. But for the multimodal approach, we have a constant R square and very high R square, even for the most difficult and complex scenarios. The second very important hit is the computational time. So here for scenario 1, 2, and 3, the ANN approach show very high computational time comparing to the multimodal approach. And here the multimodal approach offers a very constant computational time, which is very important because we know that in machine learning we need to propose we need to have a lot of time to for the proposed models to predict or to forecast something. Voilà. So here some results for the multimodal approach. So here I choose different kinds of shapes. The circle is not very easy because here we will use different kinds of muscles here because we have a circle movement, and then this movement is from down to up and then to up to down. And here we have a cursive letters, Arabic letters, and these Arabic letters show the variation of the velocity, of the orientation of the movement. And this is not very simple to estimate specifically if we will use the validation between different patients. Okay, so here I think I try to show the most important thing of the multimodal approach. The multimodal approach, in my opinion, is a solution to avoid problems for physical and also input-output driving models. With the multimodal approach, we can simplify the model and also reduce the computational time, which is very important. And here I can also open a discussion about the kind of the submodels, because it's not very simple also to choose the different submodels of the global model. Here we can put submodels that represent the different operation points, but also we can integrate submodels that take into consideration the different perturbations, the different faults that we can have in our system, etc. And we applied this approach not only for the biomedical applications, but also for some application based on the robots. If we have very noisy environment or different perturbation of my robot, we can also use this multimodal approach to avoid these problems. Thank you.
Thank you, Inès, for your nice presentation. Let me open the discussion. So whoever wants to ask questions, just either raise your hand and then ask question, or just switch on your mic and ask question.
I would have a question, if you allow. So thank you for the presentation. Could you say a few words about the ANN that you use? So how do you choose the setup for the ANN? What is that ANN taken as an input? What is an output? And what is happening in between? And why is the setup of the chosen ANN as it is? because I saw the type of signal that you try to reconstruct with the ANN. And if I remember correctly, the measured signal was kind of smooth, but the prediction of the ANN was discontinuous. So why is that, and why not differently? That's my question.
Okay, thank you. Thank you for the question. So here the input is the EMG signal, and the EMG signal is very, very unpredictable. So before applying the EMG signal as an input to predict the first estimation, we need to filter, we need to clean my data, and yes, and we apply Butterworth filter to avoid this kind of problems in EMG signals, not in the muscle. And then we will for the EMG signal, we will just take the envelope, not all the signal. So we will apply the envelope of EMG signal to predict the first muscle. So we applied the same steps for the data preparation, for the multimodal approach, and also for the ENN approach, okay? But for the ENN, we just put the parameters that was proposed in a paper, and in this paper, they prove that the most efficient approach to estimate the force muscles is the ANN approach, okay? So we take these parameters and we try to apply these parameters for the same database. We use the same database, use it in the paper, and here we compare our approach to the shown approach in the paper based on ANN. And they have, in my opinion, we can also add more and more parameters and more layers for the ANN approach to well estimate, but here we will have a very complex model.
So that means you use a feed-forward neural network for that type of prediction.
Artificial neural network, and we take the same parameters published in a paper that prove that the best one, comparing, for example, to different kinds, Hammerstein-Wiener, to Kahnen, to SVM, different machine learning models, they show that the best one is ENN. So we take the same parameters for the same database, and we show that with the multimodal, we have very high performance comparing to the ANN.
But why is the prediction the green line in your slide? Why is the green line a step function and not a smooth function?
I think it's the problem of the algorithm because as I said, the EMG signals are very unpredictable, a very dynamic signal. I think is the problem of the algorithm to follow the dynamism of the signal, because if I have switching tac, it can follow, but with the multimodal, yes, because here we have an activation function that can put the signal more smooth. This is the limitation of the algorithm, because if I have very dynamic signal for the input, I can't have a good prediction.
But the measured signal was smooth, so I'm surprised that the prediction by the ANN is kind of the stepwise function. So I was wondering whether that is a wanted outcome or an unwanted outcome.
Yeah, I will show you an example of the input. This is an example of the input, EMG signal. And here, the smooth one is the output, the force muscle, okay? So here, the first muscle is smooth, but the input is not smooth. So the algorithm, because from the input, I will predict the output, okay? So here, in my opinion, this algorithm have these problems because it can't follow the dynamism of the input. Because here, you can look. Voilà. If my input is very dynamic, the algorithm have a problem to estimate the smooth output from this kind of input, very dynamic input.
But is the ANN, is the input for the ANN, is that a time signal, a time history of an of a signal, or is that the signal at some given instant of time?
I don't understand your question.
So my understanding is you want the ANN to predict what the force is given some EMG signal. So that for me would mean I have that EMG signal at a given time instant, and that means that produces a certain force at the same time instant. And that is exactly what you want to predict.
Mm-hmm.
Yes?
Yes,
that's the
from
question.
EMG signal, I want to predict, because I just have an idea about EMG signal, I want to predict the force of the muscle for the prosthesis.
Yeah. So, okay.
And of course, we will use the force of the muscle of the previous measurement, okay? Because the patient don't have the forearm. We have amputees patient.
Yeah. So that means what we have in the x-axis, these samples simply means these are measurements over time, right? So these are the different time instances where you have an EMG signal and you have the according force signal, right?
Yeah.
So the real force is blue, so that the real thing that you measure is a continuous function over time, right? And yeah. So to go back to my question, why is the green prediction so steppy? You get my point?
Not steppy.
I think it's.
We don't have
It looks like so very small on my screen, but it looks like little stairs, you know.
No. It's not steppy. It's continuous. It's continuous, but with a lot of it's continuous. You
But
can
with
see
a lot of fluctuations.
a lot of fluctuation. C'est ça.
Okay, so if that is a time-dependent process that you try to predict with an ANN, is it then a good choice to use a feed-forward neural network? There are other types of networks that might be better suited for the time signal, if I understood that correctly.
Yeah, this is the question. So here we choose a paper, very known paper for the force estimation by Farina. He's very famous in the force estimation. So he proposed a paper, and in this paper they propose different algorithm for machine learning algorithm, statistical models to estimate the force muscles from EMG signals. And they show that this is the best algorithm to estimate the force muscles from EMG signals is ANN. And we used the same data, because if you will change the data and use this paper as reference, it doesn't work. So we use the same data and the same parameters that they put in the paper, because in my opinion, it will be better to focus on this paper, because they prove they have a very good comparative study between different algorithms. So and then we show that the best one is using multimodal approach than ANN. But here, this result is not for very simple validation. This result is for the validation between two patients, and this is very hard to validate, because even for the same person in the same condition, for example, I will take your measurement. If you will write the letter A, okay, I will take the measurement of EMG signals and the coordination of the letter, for example. And then I will redo the same test with you in the same time. I will find other kind of EMG signals. It's very unpredictable. So here, this result is for very complicated validation. Because our goal here is to improve the quality of prosthesis, because I can see 100 percent of the patient cannot use the prosthesis because they are not precise. They can use the prosthesis for 2 weeks, 3 weeks, and after they don't use. And the prostheses are very, very expensive. So here we have a problem. Huh? We have a real problem.
Mm-hmm. And from a technical perspective, how do you approach this training and evaluation of the neural network from a technical perspective? So in what sense is that implemented and trained?
If I will understand your question, so here the technical solution allow to will estimate the movement from EMG signals without any modification of the desired movement. Okay, because the patient said instead to open my hand, I find the prosthesis do this movement, close the hand, and it's not logical. So the approach can correct and estimate the good movement, but also, but not only for the very, comment dirais-je, the very known movement, closing, opening, turning hand, right, left, but also for very fine movement, like the handwriting, for example. Like, for example, I want to draw something, I want to sign. This is a very fine movement, okay? And we need to show the characteristic of each person in the drawing, in the signature, the tilt of the writing, the velocity, the pressure. We want to see this kind of properties. And we have another application not only for the prosthesis but also for the detection of the Parkinson disease. They can detect the Parkinson disease just from the handwriting, okay? And in general, they wanted to propose a system to improve the handwriting of the patient because they can use the handwriting to rehabilitate the problem of the Parkinson. This is another problem for the Parkinson disease. But in the multimodal approach, we are not just limited to estimate the good movement, but we can also put some models with the noise, with the perturbations, with the faults, because if I have a prosthesis, I will put here some electrodes, and the electrodes move because we are talking about gel electrodes, and if the electrodes will move, I will change the information because I will measure another muscle. Okay, the information will change, and I will have a not good estimation. Yeah. So here we can put in closed loop the fault in my model. I will take into in consideration even the displacement, for example, of the electrodes. Mm-hmm. I will also inject the problems of the interconnection of the cable, for example. I can have this, or for example, the perturbation of, because the amputees in general, they have some problems of tremors also for the muscle. So it's, in my opinion, it's a very general model.
Yeah, my question actually was pointing to a different aspect. I was simply asking for what package did you use to implement the ANN and to train the ANN, and what your experience with that was?
You want to, I don't understand. You mean the experimental approach, the validation, the real
No,
validation?
you said you have an ANN representation, or you trained an ANN to predict the signal, the EMG signal as an input, and the force muscle, the muscle force as an output. So that means you have an ANN somehow implemented using some package, I guess, and you definitely also have experience with the training, which you probably could share. So what is the package that you use to describe the ANN, and also what are your experiences with the training of these ANNs that you have implemented?
You mean the parameters of the model? You mean the number of layers? You mean this?
Yeah, and what package do you use to implement it, also to program the ANN, so to say?
Yeah, the detail is in the paper. Maybe I can find the paper somewhere. the different properties of the model are in the paper. Yes.
Which paper? Because you haven't
I can
shared
send.
this with us.
Okay, I can send you the paper now, the multimodal approach. Just a moment. Okay. Yep. I can send the link now.
Yes, please. You can use the chat.
Yeah.
Okay, good.
Yeah. All the details are in the paper.
So,
also the computer, you used computer, all the information are in the paper.
do I understood it right that you took this already trained model for a given data, and you used the inputs and outputs of that model, and then you repeated the procedure with your multimodal approach, or you had a new data?
No, we use, because if you want to compare something, we have to use the same data. Because if, for example, I have a very small data and to compare my approach with another approach with a lot of data and very little delay between the samples, it doesn't work. If we want to compare something, in my opinion, based on data-driven data, we must to compare the same kind of data. Because here we talk about the approach, so I can't see my approach is better if I will compare with another kind of data.
Yes, sure, but it was not clear whether you had an access to this ANN architecture libraries and you just used your data to run it through this training procedure for this ANN architecture.
The parameters of the ANN are the numbers of the epoch, the numbers of layers, etc. The different parameters were we know which kind of parameters they used, because one of the authors of the other paper is also author with us. So here we used this data with the same parameters to compare the multimodal approach. I don't know if I understand your questions or not.
Yeah, but maybe, I don't know, Andreas, do you have any more comments or questions now?
I just had a quick look at the description in the paper, and it says it's implemented in MATLAB. So I was just asking what type of software you were using to describe the ANN. And yeah, that's fine for me. Thank you.
Thank you.
Right. And may I have a short question about what you mentioned near the slide 4? You mentioned that you want to have piecewise continuous or piecewise linear models over your domain. So you split your domain into different regions, subdomains, each of which was meant to be linear, right?
This is to explain the global approach, but for this application, no, we use another kind of we just use three submodels, because before proposing the submodels, we have the data analysis, and from the data analysis we can check that we have three main kinds of data. So then we propose submodels for which kind of data. But this is the global approach, the global explanation for the multimodal approach.
Mm-hmm. And it was not clear to me what were the controlling parameters, what were the inputs to your model, whether it was just the signal from this brain activity, or it was also some feedback with the current value of force that is exerted by the muscle,
Okay.
Because for me it was not clear what was the input and how the control process was going on in time. Have you used the historical data? Was it a PID controller or different controller? What sort of input and what sort of history data you were considering when in your model? I mean, in ANN and in this multimodal approach.
For
This
the
was not
multimodal
very
approach.
clear.
Yes.
Mhm.
So for the multimodal approach, we used for the input the EMG signals. Okay.
Only EMG without any
EMG
knowledge
signals.
about the
No.
history of force or something.
No, because then if, for example, I will apply ANN, they indirectly will integrate the previous values of the force, the estimated force muscles. But no, just from EMG signals, we will estimate the force muscles. Yeah.
But
The only input is EMG
as an
signal.
input, you had a given value of EMG at a given instance of time, or you had the interval of time, so the whole trajectory of your EMG as an input, because this was not very clear
Not
to me.
clear
And
for the model.
whether you were trying to reproduce the, let's say, force trajectory versus the EMG signal for the whole domain as an input. So input was the whole trajectory of EMG. The output was the trajectory of the force, or you have this instantaneous points of EMG.
Instantaneous, yeah. Time per time, yes. Yeah. But of course we need to fix, for example, 3 or 4 values for the training of the model. But the model finally from EMG signal at this instance, I will estimate the force muscle.
But the force of the muscle is a time dependent phenomenon, right? It depends on the history of your EMG signal. And so my question is, how were you at all able to really reproduce the proper trajectory of the force without considering the history? And this is a
For
bit
example,
puzzling, but maybe I just misunderstood the concept, of course.
Yeah, I can, for example, explain by ARCS model, for example, because we tried also with ARCS model. And ARCS model here in the equation, for example, I can put f de k plus 1, f de k plus 1 is equal to the sum of the input EMG signals at k minus I plus the sum of the previous force muscle k minus g, f de k minus g. So here here I consider EMG signal at this instance to estimate the force muscle at k plus 1. Okay, and of course I will inject the estimated in the previous time the force muscle in my model. I don't know, it's clear or not.
I see. Maybe how I understand it now is that you are just estimating the increments of the force over time.
Yeah, because it's because the prosthesis will be put it in on the forearm of the patient, and he wanted to estimate at this moment this the movement. Okay. So he will move here or his hand like this, and in the same time I have to move the hand of the prosthesis. I need something in the real time. I will not consider all the database, save the database, and then estimate all the force muscle from all the EMG signals. It doesn't work for this application. I need something for the real time. And this is the challenge for this application. Because if I have the time to predict, to estimate, I will use a very more simple algorithm, because here I have models to estimate, to validate. I have also the function of validation. It's not very easy to define the function of validation. It's more difficult than the submodels. So here is the challenge in this approach.
I see. Thank you. Are there any more questions?
Jakub, hi, if I may ask something.
Sure, sure.
Thank you for your presentation. I'm not related to this field, so I would like to ask, these linear models, the submodels that you have in your library, are they the result of some type of linearization around operating points? How do you define them?
Thank you for the question. Very important question. So here, if I have a physical model with physical parameters and my model is nonlinear, so here I have to do linearization, okay? If I don't have physical model, because it's not possible to find the physical model, so here I have to go to the data and analyze my data to find the different groups of the data, and then I have to define models for each kind of data. I don't know if the response is clear. And for this reason, I present in the first time the equation of the estimation of the force based on physical equation, where we can find the mass and we can find, yes, some parameters, physical parameters. But these physical parameters can change also. If I change for activity, etc. So here, if I will talk about the physical model, I can talk about linearization of the model if the model is nonlinear. If just I have nonlinear parameters, so here I have to define the different parameters for the different models.
And this choice that you have to make, is it made automatically? How is it?
Oh no, here we have to study, and we have to study the system. It's not automatically, because if, for example, I will talk about AUV application, because we are working on the AUV, and for the AUV we have very nonlinear system, and here I have to study the equation of the system. If I have nonlinear equation, I have to know the kind of the behavior of the system that I have, and which operating point I will work on to do the linearization of the system.
So, okay, for each application, you have to create a library of models based on your knowledge of the system.
Yeah, this is very important yes, the submodels and the number of submodels are very important.
But this is something you have to define based on your applications, right?
Based on the application, yeah. If
and
I
then
have
this switching, how is it done? Is it done automatically?
Yeah, if I will go to the switching decision. So here I just want to choose the adequate model 1, 2, or 3. But if I will pass from one model to another, here I have a problem of stability. Tack, 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 the switching. This is not good. For some application, I will have a very high perturbation of my system. This is not good. So here I prefer the fusion, but the fusion, I have the other problem to define the function of a fusion.
Okay. So this is, from what I glanced through, is not addressed in your paper, how you do the fusion.
How I do the fusion? You want that I show you how I do the fusion?
Just maybe, you know,
Yeah.
paint a little picture.
Yeah. So, okay. So here, for example, here how I can choose my models, because here in this paper I just present the approach based on the data. Okay. So here after study the data, here we can see three kinds of data, and from these groups of data we define a model for each kind of data. Okay. And then for the fusion, data analysis, I forget. Okay, so I will start by the final equation here. So here, for example, the force muscle is the sum of a parameter multiplied with the Fi for each one. And here, voila, here this mu, this parameter is the inverse of this error. And this error is what? Is the normalized error between the estimated one and the real one, okay? If you want, Voilà. This is the equation how I can estimate the parameters in the real time, because here I need real time estimation. I need real time estimation by R square and with forgotten time, fixed with forgotten time. And just I want to go to, voilà. Okay, so for this paper, here I have submodels 1 to n, for example. So these models have fixed parameters, and then fixed parameters with fixed input and output. So for first time, I will apply, for example, here the EMG signal that I want to apply to estimate the force muscle. So here I apply this signal to the submodel 1 with known parameter. And then here I will have F11, okay, the estimated force when I apply my EMG signal to this submodel, defined submodel. And then here I will compare the difference between these forces, okay, to have an idea about the error. Okay, if I know the error, I will do the absolute value, and then I will compute mu11 is the inverse of the error. Why the inverse of the error? Because if I have a very low error, so the model is very good for me. I want to represent very well this model. So here I have to put the inverse of the error to highlight this model, okay? And then I can finally compute 1 force or 2 force or even 3 forces on the same time.
And then you blend the errors. Okay, you use the errors to determine the blend.
Yeah, in this function, yes, it's based on the error. For example, I have another paper. We put exponential term to have comment dirais-je, because to make the error tend vers zero, because we have a problem with the error. We have another kind of models, and the models were, yeah, and the error were not very descriptive for the contribution of the model. So here we have to refine and to add something. Yeah.
Okay, thank you. Thank you for your question.
Thank you for the question.
All right, we are approaching 11 a.m. So I think it's a good time to finish, unless there is a short question, but I don't see it. So perhaps there will be a question later offline. Thank you so much, Inès, for presenting us your approach and the comparison, and for the discussion. And thank you to everybody for your attention and for the discussion as well. So have a good day, and I will keep you posted about the future seminar meetings.
Thank you very much. Thank you. Merci. Au revoir.